Well, the next thing I want to visit with you about are just some concept problems here. You can see here in this one picture from our textbook about this gentleman towing pushing this wheelbarrow. Where do you think you should position the center of gravity of the wood to make it the easiest to push or the easiest to hold? And I think everybody could probably guess that if you have the center of gravity too far forward, then it's going to be unstable and it's going to tip too far back. If you have the center of gravity too far back, it's going to make it really hard to hold on to. So someplace up in here where you're still having to put some force and it's still, but it's not unstable and meaning too far forward, that's probably a good place to put it. And maybe that's pretty obvious. How about this one? If you were trying to pull this little four-wheeler up the ramp, let's say that you had a maximum force that you could apply, and what we want to do is analyze this in the spot that it's in right now. In other words, not after it gets onto the bed of the truck, but right now where it's on this ramp. Where should you attach the rope? Should you attach it at A and pull that way, or should you attach it at B? If you're working with a group, I'd like you to stop and pause and just consider, where would you get the maximum benefit from your force? Again, you can only lift, or you can only have so much tension in that force in order to get it up the hill. So where should you attach it? All right, well, let's consider. If I attach it here, it's obviously pulling in a straight line. If I attach it here, it is pulling up at an angle. Let's draw a couple of free body diagrams of this with this force at two different locations and see what it looks like. All right, so here's the first free body diagram where I've attached it at the bottom. I'm pulling up at an angle. We know enough about inclined planes now that there's an mg going down, mg sine theta. It looks like that. In the x prime direction as we're going up here, my ability to pull, say I have a maximum p, my ability to pull up here is limited by p cosine theta. Obviously I have an mg sine theta. However, if I attach it up here, I get the full benefit of p. This is more effective because it's not reduced, the angle or the force here is not reduced by some angle component. So this is actually a better place to attach it. And I doubt that very many people got that the first time. This always feels to most students that that's a better place, but this is actually more effective in this position. So I hope that you can see that. Well, here's a little experiment regarding this broom. So this is a fairly ordinary broom, but what we're going to try to do is find the balancing point. And you can see here that it balances pretty well at about that point. Clearly it's not super steady, but your objective is to find the balancing point when I give you some dimensions. So let's go ahead and try that. Well, here's a little concept question. This broom head weighs 10 pounds. And the broom handle is 5 feet long and it weighs 1 pound per foot. See if you can find the point of balance. It'd be out in here someplace. And then once we find that, we'll find out which side weighs the most. So go ahead and pause this and work this out by yourself or with your neighbor and see if we can find out the point of balance. Okay, let's walk through the solution real quickly here. And what we have is, we can do this in more than one way, but I'm going to do it with one moment equation about point A over here. We're going to say that balance is at point B. All right, let's sum the moments about A and see what we can find. Sum moments about A equals 0. All right, the broom handle weighs 5 pounds. The center of gravity of the broom handle is 2.5 feet from the end. So that is going in the negative direction, 5 times 2.5. The head of the broom, it weighs 10 pounds, and it's also going in the negative direction, times 5 feet. And then the balancing point up there, B, and we have some distance x bar that we're looking for, and that's going to be x equals 0. Now, what is B? B, if I sum the forces in the y equals 0, I can see that B is equal to 15 pounds. When I plug that into there, I can solve this for x is equal to 4.167 pounds, or 4.167 feet. And so there's the answer. That's probably the easiest approach to go about doing that. There are obviously multiple ways of doing simple equilibrium problems like this, but this is probably the most straightforward. All right, now which side has the most weight? The left side or the right side? Now think about that for just a second, and let's see what we've got. All right, well, the left side is only the broom handle. The broom handle weighs 1 pound per foot. I have 4.167 pounds, or feet. Therefore, the left is equal to 4.167 pounds. The right-hand side includes that whole broom handle, or the broom head. So clearly the right is much heavier. So it doesn't balance by virtue of one side being heavier or not. It is all to do with the moments and the lever arms. And I think you know that, but this is just to reiterate that. Now here's two problems that look very similar, but they're not the same. Let's look carefully at the way these problems are drawn. On the right-hand side, this is a beam. We should recognize this now as a pin connection. We should recognize this as a two-force member. So this is a straightforward two-force member problem, if you will. Two pins, or a pin on each end of the two-force member. Over here, I don't see a pin over there, and I don't see a pin over there. In fact, I don't see any pins anywhere. What I see is this thing being nailed to the wall and actually trying to be pulled out of the wall. So in this case, this is not a two-force member problem. This is much more of a simply supported or a cantilever beam problem, or something like that. Or it could be a simply supported problem. I think we'll just call this a simply supported problem. Let's look at what the reaction over here might be. In other words, if I say that this is a pin here, I would have a BY and a BX. If I say that that is a roller, I would have an AX over here. And clearly there's some weight over here. So this is much more of a pin and roller kind of problem over here than this being a two-force member problem. So look carefully at the pictures and make sure we kind of understand how they work as you try to solve for the unknowns. Well, the last thing I want to do here in this section is talk about these collars, which are, I call them special supports. There's not a real big emphasis in this course with collars, but you should understand what the reaction might be and how they work. So a collar often is considered frictionless on this surface. In other words, they're free to slide back and forth. Obviously, a roller has no ability to receive any force in this direction or any moment. Now look carefully at right in here. What this is if this was a pin and it had no ability to resist moment here, if that was a pin, it would just fall straight down. But it doesn't do that because this has the ability to resist moment. So let's go ahead and draw the reaction here. Again, there shouldn't be any forces in the y, but there should be some force in the x, and there is some ability to resist moment. So let's go ahead and draw what I've done is on these problems I've drawn a portion of the free body diagram over here so we can draw that. So I'm going to say that there will be an AX and a moment. Well, first of all, there should be a reaction force or a resultant force of all that. There should be a BY, and there should be some ability for a moment like that. And there is our free body diagram for that. And then when you sum the forces in the X and Y, you should be able to solve for all those things. This next one down here, here's another collar, but in this case it has a pin. Again, in this direction they are free to move, but because there's no ability to resist moment, it has it's free to rotate. So the only force it's going to have here is just in the x direction. So let's go ahead and draw the reaction forces here. I've got those two forces. I got the AX. I know that there's only going to be a BX here, which means that the AX is going to go this way. And that will be the complete set of forces and free body diagram for that. Alright, this next one is a little bit odd, but we're going to consider it anyway. In this case, we have something very strange. This is a roller on a vertical wall. Means it has no ability to resist any moment in this, any force in the y direction, but clearly it can resist force in the x direction. Because this is a pin, it has ability to rotate there, but over here there is no pin. So this one will have resist a moment. Because this is a slider over here, it should have no force in this direction. The only force would be perpendicular to the frictionless surface. So let's go ahead and draw all of the forces. It's going to be a B this way. There will be a moment at B. Let's call this moment at B. And then B normal, whatever that is. Then over here, the only force we'll have will be an AX. Anyway, there should be enough geometry and stuff to solve for those reactions, but that's what they should look like.